This lesson is on radicals, also known as roots. Roots go back to the age-old question of how to find a side of a square given its area. So let's say the area of this square is 9. Can you tell me what the sides are? Well, we know that we're taking the side times itself in the case of a square, and that should be 9. Therefore, how do we reverse this step? In this case, well, we know that 3 times 3 is 9, so since 3 squared is 9, we know that the square root, the opposite of squaring, is 3. But what if this 9 was a 10? Would it be as easy to find? Of course not. So over the years, there have been many attempts at various methods of approximation. Today we have the calculator. But this question has been of great importance in the life of mathematicians. It has also extended to other dimensions, not just squaring, but cubing, taking to the power of 4, 5, 6, and so on. In the case of cubing, we can still imagine a picture. Say the volume of this cube is 27. Well, the question then would be, what is the length of the side of the cube? Well, since it's a cube, we're going length times width times height to get at the volume. Meaning if they're all the same, that's the same as saying x cubed is 27, and therefore what is x? The what is x is given by the cube root of 27. So you can see that rooting is a reverse process of taking to the power of n. So let's take a look at this general radical, an nth root radical of a. The radicand is the number underneath the root or the letter. You've got your radical sign, and you've got your index, which is also called order or degree. So let's look at simplifying radicals. So simplifying radicals, you want to find the number that basically goes back on the process. So remember that taking something to the power of n will give you a, and then taking the nth root of a will give you the number back. So they're just direct opposites of each other. So in this case, what is the root of 16? Well, we know that 4 squared is 16. Therefore, we know that root 16 should be 4. But hey, wait a minute, isn't negative 4 squared also 16? So shouldn't this also be negative 4? Well, yes, those are two possibilities. The positive answer is called the principal root. And for our purposes, we mostly stick to the principal root. This is called the negative root. And it is a possibility, but we're going to stick to using principal roots. So let's continue. What if you have the 4th root of 16? Well, it's like saying what to the power of 4 is 16. Now, you can use your calculator, but you can also see that 2 times 2 times 2 times 2 would be 16. So we know that 2 to the power of 4 is 16, and therefore the 4th root of 16 is 2. Now again, it could be negative 2, but since we're only looking at the principal root, it's just a 2. Now, what if you have 4th root of negative 16? So it's saying x to the power of 4 is negative 16. So we're looking for a number that when we take it to the power of 4, we get negative 16. Well, is that even possible? Think of squaring, or taking to the power of 4, or taking to the power of 6. If you write that out, there are 4 x's being multiplied by each other. If they're all positive, it'll result in a positive. If they're all negative, each 2 will become a positive, and so the answer is always going to be positive. And it's impossible to get a negative, so this actually does not exist. So you can write DNE for does not exist. Okay, well, what about cube roots? So by definition, we're saying, well, something to the power of 3 is 8. So we're looking for a number that multiplies by itself 3 times to give you 8. And I mean, you can factor this out and see that 8 is 2 times 4, 8 is actually 2 times 2 times 2. And so that's 2 cubed. So 2 cubed is 8, and so therefore cube root of 8 is 2. Now here we have another negative under the root, but it's a cube. So notice that x cubed is negative 8. So that means there's 3 numbers being multiplied, the same numbers being multiplied by themselves 3 times, to give a negative. So what sign would you think needs to be there? Well, we have negative times, if it was positive, positive wouldn't work, but negative times negative will actually result in a negative. So this actually works. But what number do we need? Well, it's a 2, right? So negative 2 would be the answer there, and that's because negative 2 cubed is negative 8. So we can notice that we have a few observations to make here. An even root of a positive number will give you a positive answer. That's because we're choosing the principal root. An even root of a negative number, like here, does not exist. An odd root of a positive stays positive, and an odd root of a negative stays negative. So the odds are like totally fine, but it's the even root that has a problem with its sign there. So here are some more examples. So we've got an odd root of 5 of a negative, so that's okay. We just know that it's going to be negative. So we're looking at what times itself to the power of 5 is going to give us 32. Now, sometimes it's easier to break it down into factors or rewrite it as a power. So we can just factor it to see what happens. So this is 2 times 16, and we know that 16 is 4 times 4, which is 2 times 2 and 2 times 2. So really 32 is 2 to the power of 5. So we've got fifth root negative 2 to the power of 5. And so you'll notice that because it's a fifth root, we're saying what to the power of 5 gives us this number. Well, we've already found what to the power of 5. That's negative 2. Again, it's nice to write your numbers as powers if possible, or as powers of products of powers. So 8 is actually 2 cubed, and 27 is 3 cubed. So you'll notice that this is the same as saying cube root of 2/3 cubed. And so if your question is what cubed gives you 8 over 27, well, that's 2/3. What do you think this one's going to be? Well, 5 to the power of 2011, and then this root here, this bit here is actually asking you what to the power of 2011 will give you this answer. Well, 5 to the power of 2011 will be this number, so that's just a 5. Now let's take a look at this example. We've got an even power here and an even power here. So notice that because this outside power is an even power, we can't have a negative inside. And we actually don't, because when we take this and evaluate it, we actually get the 10th root of negative 3 to the power of 10, which is whatever 3 to the power of 10 is, because if you multiply a negative by itself 10 times, you get a positive. And so therefore, to answer what to the power of 10 is 3 to the power of 10, well, that's 3. Now in this case, this is an odd exponent and index. So even if you evaluate this, you'll actually get negative as an answer in here, and then 3 to the 9. So because you're taking the 9th root, your answer is then negative 3. So let's generalize this. If n is even, so if your index is even, you're taking the nth root, an even root, you'll notice that you're always going to be ending up with a positive answer for your value. So we looked at a couple examples, and what all this means is if your x is positive, then keep it positive. If your x is negative, that's what this less than 0 means, then take negative negative x, right? So if x was negative 2, for example, so an even root of negative 2, so by this definition, it would fall under the negative case, in which case you'd have negative negative 2 in there. So that's actually positive. So either way, this is actually a definition for absolute value. So either way, you're ending up with a positive answer. Note that you can't get a negative answer out of it because we can't take an even root of a negative anyway. That doesn't exist. Now, if n is odd, you'll notice it's fine. You could have a negative, it stays negative. You could have a positive and it stays positive. And that's coming from the fact that the odd root will be negative for negatives and positive for positives. So let's take a look, a couple examples here. If you have a variable and you take the root, say, of the square, so square root of a square, so that's actually technically going to be written as absolute value of a. Eventually we just assume that the variables are positive, but in this case, because we're just starting to get into it, let's just keep that as a scenario. So x to the power of 6, square root of that, well, that's the same as square root of x cubed squared, because x cubed times x cubed gives you x to the 6. And so that's really the same as absolute value of whatever x to the 3 is. Now, because it's cubed, it won't necessarily be positive, so we need the absolute value bars there. So similarly here, we have negative x to the power of 4. So because it's an even, we need the absolute value of its answer, but taking the absolute value of negative x is the same as saying absolute value of whatever x is. And same here. Now, because it's a cubed, so we don't need to have an absolute value because it's an odd exponent that we're dealing with here, so it's just going to be equal to y. Here's another even exponent. This negative is up front, so it stays negative, and then what's happening is now we're taking the 8th power and the 8th root, leaving us with absolute value of negative x, which is the same as negative absolute value of x. 5th root, notice we don't need to have anything special. However, we know that this here is negative, so okay, so we've got our first negative, and then we've got this negative. 5th root of a negative will be negative, and then we've got x to the power of 5 in there, which when simplified is just x. So two negatives make a positive in this case, so it's just x. Now, approximating radicals is also useful, especially when you want to graph radical functions, or if you want to get a better sense of what it is as a decimal in applications. So you can pull out your calculator and type in the square root of 3 and you should get 1.73. Now, our calculator has a method programmed inside of it to calculate this. What about the 5th root of 100? So try on your calculator. If you have a TI-83, you'd actually want to first type in 5 and then go to math, power of, and then 100. So that's 2.51. So these are approximations using your calculator, so make sure you can find those. Now, sometimes you can just approximate based on your knowledge of what the perfect squares are. So 70 is close to 64, which is 8 squared. So what's 9 squared? 9 squared is 81. So is it How is it in relation to 64 and 81? Is it closer to one of them? Well, it seems a bit closer to the 64, so that I would say approximately 8.3, because 8.5 would be right in between. So you can also kind of approximate mentally like that. So 115 is between, well, 11 squares 121, and 10 squares is 100. So it's in between there, and it's pretty close in between. So I'd say 10.5. So what do these functions look like when we graph them? If we want to graph out all the possibilities for what it is, then what do we get? So if you have a function, and remember, it wouldn't be a function if we weren't considering only principal roots. We're only considering principal roots. So notice that our y is like an f of x. So if we input, say, 1, we get square root of 1, which is equal to 1. So that's 1 point. 2. Well, you could use your calculator to approximate the square root of 2, and you'd get 1.4. So at 2, it's about there. And with these, especially, because you know it's not going to be a line, make sure you graph a lot of points. 3, the square root of 3 gives you 1.73. When does it hit 2? Well, 4. The square root of 4 is 2. And then the square root of 5 keeps going, 2 point something, and so on. Okay, let's go the other way. What about 0? At 0, square root of 0 gives you 0. What about negative? Negative 1. Square root of negative 1. Oh, wait. We weren't allowed to do those, were we? Nothing squared will be a negative ever. Therefore, we can't have a square root of a negative. So this impacts our domain. Notice that our domain is everything from 0 all the way to infinity. Now notice that if we had been including all the negatives, that would have been a sideways parabola, because a parabola is y equals x squared, and when you take the root, it's actually flipped around because it's the opposite process. But since this would not be a function, so this is another reason why we only include principal roots. Now, what does the basic graph of a cube root look like? Remember, cube root doesn't have this domain issue. So if we plot some points, you can go ahead, this is your f of x. Start with 0, say, well, cube root of 0 is 0. 1, cube root of 1 is 1. Cube root of 2 is 1.26, and so on. When do you think it hits 2? Well, that'd be whatever 2 cubed is, so that's actually in 8 spaces way over here. So it is quite slow in its growth like that, but you can find more points and find the rest of them. But now, remember that all of these could have been negative, and the answer would just have become a negative. So all of these points transfer into these negatives in the same way. So try to find more points and convince yourself that this is what it looks like. So now you can say that, well, we know the domain of the cube root function is all real numbers. What about the range? Well, you can imagine that this will grow. It's just growing really slowly. And same with this. So the range is also all real numbers. But the range here is restricted because of the principal root issue. So it's 0 and greater. Now, a really cool site to check out instead of your graphing calculator is Desmos.com. That's www.desmos.com. So it gives you a graphing pane like this. And say we want to take a look at a root function, so a root of x. it shows you that. Now what I want to explore with you here is what happens when you put other numbers in here. So play around with it. What if you add 1? How did the graph change? What if you add 1 like this? How did the graph change? What if you multiply it by 2? How did the graph change? Multiply it by 0.5. How did it change? So play around with different changes and look at the patterns. So I'd like you to go to this site and just play around with it. So there's the square root function again. Now let's do a cube function. So we go to more, cube root of x, and you can see that this is what we were kind of approximating. It shows you that that's 1, 1, and it's got a bit of a different curve there. So when you're graphing, make sure you graph completely. Now what happens if we take this and add 1 to it? Didn't it shift to the left? Isn't that weird? Why is that? What if you add 1 like this? Oh, it went up by 1. So play around with that. What if I type in -2? What do you think it will do? Oh, it went down by 2. What if you expand it? Right? So that means if you put a 2 there, that means you're actually doubling all your answers, so you can imagine that happening. +5. Oh, it's up there now. So play around with this and try to come up with a strategy of seeing what the graph's going to look like based on what you see.